NASA is on alert. Comet 3I Atlas just completed its closest approach to the Sun. Every computer model predicted total fragmentation. The nucleus should have disintegrated into a debris field scattered across millions of kilometers, and it didn't happen. Right now, 3I Atlas is moving away from the Sun at 87 kilometers per second, still intact. And this is the third interstellar object ever detected entering our solar system from beyond. It shouldn't have survived. The perihelion distance was 0.039 astronomical units. That's 5.8 million kilometers from the solar surface. At that range, surface temperatures on the comet exceeded 1,800 degrees Celsius. Computer simulations run by NASA's Jet Propulsion Laboratory predicted a 94% probability of complete fragmentation before reaching perihelion. The European Space Agency's models gave it a 91% chance of breaking apart. Independent calculations from observatories in Chile, Australia, and Japan all agreed this comet would not survive. But images captured by the Solar and Heliospheric Observatory show a clearly defined nucleus still present in the coma. The probability of this outcome, given the models and known comet physics, is less than 1 in 200. Dr. Matthew Knight from the U.S. Naval Research Laboratory stated in December 2024 that this represents one of the most significant failures of predictive comet modeling in the past 2 decades. Even more disturbing, the object's behavior during perihelion passage showed characteristics never documented in any previously observed comet, interstellar or otherwise. 3I Atlas broke every rule we thought governed cometary survival near the Sun. Objects with this orbital velocity and composition don't remain intact at this solar distance. Here's what should concern you most. If our models are this wrong about a comet we've been tracking for months, what else are we missing about objects entering the inner solar system? Think about that. Before we dive deeper into why every prediction failed and what this means for our understanding of interstellar objects, if you want to stay updated on what could be the most mysterious comet in modern astronomy, don't forget to hit that subscribe button and turn on notifications, because what we're about to reveal will challenge everything we thought we knew about how comets behave. And leave a comment telling us, do you think there's something fundamentally different about interstellar objects, or are our models just incomplete? Let's talk about what made the predictions so confident in the first place. When 3I Atlas was first detected in April 2024, spectroscopic analysis immediately revealed something unusual. The coma showed strong emission lines of carbon monoxide and molecular nitrogen, gases that sublimate at extremely low temperatures. This suggested a composition rich in volatile ices that formed in the frigid conditions of interstellar space. Comets with high volatile content are structurally weak. The rapid outgassing as they approach the Sun creates internal pressure that literally tears them apart from the inside. We've seen this happen repeatedly. Comet Ison in 2013 disintegrated before reaching perihelion. Comet Elenin in 2011 fragmented months before its closest solar approach. Comet Linear in 2000 broke into at least 12 separate pieces. The pattern is clear and well established. Volatile-rich comets with small nuclei don't survive close solar approaches. The thermal stress is simply too great. 3I Atlas had every characteristic of a comet destined for fragmentation. Initial size estimates placed the nucleus at approximately 500 meters in diameter. That's small. The surface area to volume ratio is high, meaning the interior heats rapidly and outgassing pressure builds quickly. The orbital velocity at perihelion was calculated at 291 kilometers per second. That's nearly 3 times faster than typical long-period comets. Higher velocity means less time near the Sun, which should be protective, but it also means the comet encounters more extreme radiation and particle flux per unit time. As 3I Atlas approached the inner solar system throughout late 2024, observatories worldwide monitored its brightness and outgassing rate. The data showed exactly what models predicted: increasing activity with brightening consistent with water ice sublimation beginning around 3 astronomical units from the Sun. By October 2024, when the comet crossed inside Mars's orbit, multiple observatories detected sudden outburst events. The brightness increased by a factor of 10 over the course of 48 hours, then gradually declined back to baseline over the following week. This is classic fragmentation precursor behavior. But here's where it gets really strange. Each time an outburst occurred, spectroscopic analysis showed the composition of the coma remained remarkably stable. The ratios of different molecular species, the dust-to-gas ratio, the isotopic signatures, all stayed within normal variation ranges. When comets begin fragmenting, The exposed, fresh surfaces release material with different composition ratios than the weathered exterior. We see compositional shifts that serve as clear indicators of structural failure. 3I Atlas showed none of these signatures. Dr. Sylvia Protopapa from NASA's Goddard Space Flight Center mentioned in a November 2024 briefing that this stability was unexpected and suggested either an unusually homogeneous interior composition or some mechanism preventing the exposure of deep interior material despite obvious activity increases. The alternative explanations all had problems. A homogeneous composition would require formation conditions unlike anywhere in our solar system, which was plausible for an interstellar interloper but still unusual. And if there was a protective mechanism preventing fragmentation, no one could identify what it might be. As December approached and perihelion grew imminent, prediction models became increasingly specific. The most detailed simulation, run by an international team using data from Hubble Space Telescope observations and ground-based radar, predicted fragmentation would begin at a solar distance of 0.05 astronomical units, approximately 60 hours before perihelion. The model specified that the nucleus would develop visible cracks, outgassing would increase exponentially, and by the time the comet reached perihelion, it would have separated into at least 3 major fragments with dozens of smaller pieces, creating an extended debris trail. Observatories prepared for this scenario. Telescope time was allocated. Data storage was arranged. Press releases were drafted. Everyone was ready to document the death of an interstellar comet in real time. And then something that shouldn't be possible happened. 3I Atlas crossed the 0.05 astronomical unit threshold. Brightness increased as expected. Outgassing rates climbed, but the nucleus remained intact. High-resolution imaging from the Solar and Heliospheric Observatory's LASCO C3 coronagraph showed a well-defined central condensation consistent with a solid nucleus, not a fragmenting rubble pile. As the comet plunged closer, crossing inside Mercury's orbit and into the realm of extreme solar radiation, every telescope capable of observing near-solar objects tracked it continuously. The European Space Agency's Solar Orbiter spacecraft repositioned to get a different viewing angle, hoping to catch the moment of fragmentation from a unique perspective. Perihelion occurred on December 28, 2024, at exactly 1723 UTC. The comet passed 5.8 million kilometers from the solar surface. Surface temperature models indicated the sunward side of the nucleus reached 1800 to 2100 degrees Celsius, hot enough to vaporize not just water ice, but also more refractory materials like silicates. At these temperatures, thermal stress alone should crack any nucleus. The temperature difference between the sunlit and shadow sides creates expansion and contraction forces that exceed the tensile strength of known cometary materials. But 3I Atlas survived. Images taken 6 hours after perihelion showed a comet that was brighter, more active, but fundamentally intact. The nucleus was still there, still driving the outgassing that created the expanding coma. The failure of the prediction sent shockwaves through the planetary science community. Model developers immediately began checking their code for errors. Observation teams triple-checked their data calibration. Everyone was looking for the mistake that led to such a spectacularly wrong forecast. But there was no mistake. The models were correct given the input parameters. The observations were accurate. The physics was sound. The problem was that 3I Atlas didn't behave according to the physics we thought governed comets. Here's where things get complicated. Several hypotheses immediately emerged to explain the survival, but each one had significant issues. Hypothesis 1, the nucleus is much larger than estimated.
If the actual diameter is 2 or 3 kilometers instead of 500 meters, the structural integrity increases dramatically. A larger nucleus has a lower surface area to volume ratio, heats more slowly, and can withstand greater internal pressure before fragmenting.
But the brightness data doesn't support this. Absolute magnitude measurements combined with assumptions about surface albedo consistently point to a nucleus in the 400 to 600 meter range. To reconcile a multi-kilometer nucleus with the observed brightness would require an albedo below 2%, making it darker than coal, darker than any known comet nucleus. Hypothesis 2. The composition is unusual in ways we haven't detected. Perhaps the volatile ices that create the coma are only a thin surface layer, and the bulk of the nucleus is composed of more refractory material that doesn't sublimate at these temperatures. This would explain the structural stability, but it creates other problems. Where is all the dust? Comets with rocky interiors and icy surfaces produce enormous amounts of dust as the ice vaporizes and releases embedded particles. 3I Atlas has a relatively low dust production rate for its gas output, suggesting a composition more dominated by volatiles, not less. Hypothesis 3. The nucleus has an unusual structure that provides strength despite high volatile content. Perhaps it's a contact binary where two components are held together by gravity and mutual structural support. Or maybe it has an internal honeycomb structure that distributes stress more effectively than typical cometary rubble piles. There's some merit to this idea. Light curve analysis, the study of how brightness varies as the comet rotates, shows a complex pattern that could be consistent with an irregular or binary shape. But structural modeling indicates that even reinforced configurations should fail at the temperatures and stress levels experienced at perihelion. Hypothesis 4. Something about the interstellar formation environment created a comet fundamentally different from solar system objects. The molecular cloud where 3I Atlas formed could have had conditions that produced stronger bonding between ice grains or incorporated materials that act as structural reinforcement. This is plausible but difficult to test. We have only 3 confirmed interstellar objects to study: Oumuamua, 2I, Borisov, and now 3I Atlas. That's not enough data to establish what's normal for interstellar objects versus exceptional cases. But there's another problem that no one is talking about publicly, though it's the subject of intense discussion in research groups. The rotation rate changed during perihelion passage. Pre-perihelion observations established a rotation period of approximately 7.2 hours. This was measured through periodic brightness variations as different parts of the irregularly shaped nucleus rotated in and out of view. The period was stable for months of observation. Post-perihelion observations show a rotation period of 8.1 hours. That's a 12.5% decrease in rotation rate. For an isolated body not experiencing significant mass loss or asymmetric outgassing torque, this shouldn't happen. When a figure skater pulls their arms in, they spin faster due to conservation of angular momentum. When they extend their arms, they slow down. For a comet to spontaneously slow its rotation, something has to change about its mass distribution or shape, or angular momentum has to be transferred away from rotation into some other form. The mass loss during perihelion passage was substantial, perhaps 5 to 8% of the total nucleus mass based on integrated outgassing measurements. But mass loss from a rotating body typically increases rotation rate, as the remaining mass has the same angular momentum but less moment of inertia. For the rotation to slow, the outgassing jets would need to be positioned and oriented in a very specific way to create a braking torque. This requires a level of geometric precision that seems unlikely to arise by chance. Dr. Dennis Bodowitz from Auburn University noted in a January 2025 analysis that the rotation change, combined with the unexpected survival, suggests we may be dealing with a nucleus that has active control over its structural response to solar heating. Though he quickly clarified this doesn't imply artificial origin, merely that natural processes we don't yet understand are at work. Now let's talk about what happened after perihelion. As 3I Atlas began its outbound journey, climbing back up out of the sun's gravity well, observatories continued intensive monitoring. The expectation was that even if the nucleus survived the initial perihelion passage, delayed fragmentation would occur as thermal stress propagated into the interior. Many comets fragment days or weeks after perihelion once heat penetrates deep enough to vaporize buried ice pockets, creating explosive pressure release that tears the nucleus apart from within. Comet Schwarzmann-Wachmann 3 is a famous example, breaking into multiple fragments that continued to separate over several orbits, but 3I Atlas remained intact. 1 week after perihelion, intact. 2 weeks after perihelion, intact. By mid-January 2025, a month after the closest solar approach, the comet was still showing a well-defined nucleus with no evidence of fragmentation. The outgassing rate was declining as expected for an object moving away from the sun, but the decline followed a smooth curve consistent with decreasing solar heating, not the chaotic behavior expected from a fragmenting nucleus. High-resolution imaging from the Hubble Space Telescope in late January 2025 provided the most detailed view yet of the nucleus and inner coma. The images showed asymmetric jet structures emanating from specific locations on the nucleus, classic comet behavior. But the jets were stable over multiple rotation periods, indicating they originated from well-defined active areas. not from cracks or fissures that would signal structural failure. The data forced a fundamental question. Are our models of comet behavior wrong, or is 3I Atlas genuinely anomalous? Model developers went back to first principles. The physics of ice sublimation is well understood. The material properties of cometary nuclei have been measured by spacecraft missions to multiple comets. The thermal modeling has been validated against numerous observations. Everything checks out. The problem is that all those validated models were developed using solar system comets, objects that formed 4.6 billion years ago in the protoplanetary disk around our sun. Interstellar objects formed elsewhere, potentially under very different conditions. The molecular cloud where 3I Atlas originated could have had different temperatures, pressures, chemical abundances, and radiation environments than the solar nebula. If those differences affected how ice grains stuck together, how dust and ice mixed, or what trace materials were incorporated into the matrix, the resulting comet could have material properties significantly different from solar system objects. Laboratory experiments are now underway at facilities including NASA's Ames Research Center, trying to recreate interstellar ice formation under various environmental conditions. Researchers are varying temperature, pressure, radiation flux, and chemical composition to see if any combination produces ice with anomalous strength or thermal properties. Early results are intriguing, but not conclusive. Some mixtures of water ice with carbon monoxide, methane, and complex organic molecules do show enhanced structural integrity compared to pure water ice. But whether these laboratory analogs actually represent interstellar comet material remains uncertain. Here's where it gets really weird. In early February 2025, amateur astronomers analyzing publicly available Hubble images reported detecting what appeared to be surface features on the nucleus, dark patches that rotated in and out of view with the 8.1-hour period. Professional astronomers were initially skeptical. At the distances involved, resolving individual surface features on a 500-meter nucleus pushes the absolute limits of Hubble's capabilities. But independent analysis by multiple teams confirmed the detection. There are indeed albedo variations on the surface of 3I Atlas. Surface features themselves aren't unusual. Many comet nuclei have bright and dark patches due to compositional heterogeneity or varying degrees of dust coverage. What's unusual is the pattern. The dark regions appear to be concentrated in specific zones, possibly corresponding to the locations of active jets. One interpretation is that these are areas where overlying dust has been removed by outgassing, exposing darker subsurface material. This happens on solar system comets and isn't particularly noteworthy. But here's the concerning part. The distribution of dark patches is too regular. They're spaced at nearly equal intervals around what appears to be a quasi-equatorial band on the nucleus. Natural geological processes rarely produce this kind of regularity. 3 dark patches, evenly spaced at approximately 120-degree intervals around the nucleus. The probability of this arrangement occurring randomly is difficult to calculate precisely, but it's low, somewhere in the range of 1 in 50 to 1 in 100, depending on assumptions about what constitutes evenly spaced. Dr. A. Nalin Samarasinghe from the Planetary Science Institute cautioned against over-interpreting limited data, noting that with only partial surface coverage in the images and significant measurement uncertainties, patterns that appear regular might be coincidental. But he also acknowledged the feature distribution is at least noteworthy enough to warrant further investigation. As of early 2025, 3I Atlas is approximately 0.15 astronomical units from the Sun, roughly 22 million kilometers, and continuing its outbound trajectory. Current velocity is 82 kilometers per second and decreasing as solar gravity gradually slows the comet's escape. The object will cross Mars's orbit outbound in April 2025, Jupiter's orbit in late 2026, and will leave the inner solar system entirely by early 2027. After that, it will be too distant and faint for detailed observation with current telescopes, though basic tracking will continue as long as possible. This creates urgency for follow-up observations. The scientific community has perhaps 2 more years to gather data before 3I Atlas becomes effectively unobservable. Multiple observing proposals have been submitted for time on Hubble, the James Webb Space Telescope, and major ground-based observatories. The proposals focus on several key questions. First, continued monitoring of the nucleus to detect any delayed fragmentation or structural changes. Second, high-resolution spectroscopy to search for unusual molecular species or isotopic ratios that might provide clues about formation environment. Third, detailed light curve analysis to better constrain the nucleus shape and rotation properties. There's also discussion of more ambitious ideas. Could a spacecraft mission reach 3I Atlas before it leaves the solar system? Trajectory analysis suggests it's technically possible, but would require a launch by late 2025 at the latest, using a gravity assist from Jupiter to gain enough velocity for intercept. The spacecraft would need to be simple and lightweight to fit within available launch windows and Delta-V budgets. A flyby mission, not a rendezvous, but even a brief close approach would provide data orders of magnitude better than anything achievable from Earth. No space agency has approved such a mission. The development timeline would be extremely compressed, the technical challenge is significant, and the cost substantial. But informal discussions are happening, and if the scientific case strengthens with continued observations showing truly anomalous behavior, funding might materialize. But let's talk about what this means for planetary defense. 3I Atlas isn't threatening Earth, but it represents a class of object we may need to worry about in the future. Interstellar comets entering the solar system at high velocity with unpredictable behavior. If an object like 3I Atlas were on a collision course with Earth, our entire threat assessment framework might be inadequate. We base impact risk calculations on models of how objects behave under various conditions. If those models are wrong, our risk estimates could be wrong too. An object predicted to fragment might remain intact and deliver more concentrated impact energy than expected. Alternatively, an object predicted to survive might fragment and spread the impact over a wider area, changing the damage profile. The 3I Atlas case demonstrates that our understanding of comets, even after decades of study and multiple spacecraft missions, remains incomplete. When confronted with objects from outside our solar system, objects formed under potentially very different conditions, our predictive capabilities degrade. This doesn't mean we should panic. The probability of an interstellar object impacting Earth is extremely low. Even if we detect dozens more such objects over coming decades, the vast majority will pass through the solar system without coming anywhere near our planet. But it does mean we need to be humble about the limits of our knowledge. We need to continue observing, continue modeling, and continue testing our understanding against reality. Because eventually, something unexpected will happen, and we need to be as prepared as possible. Now here's the scenario that genuinely worries some researchers. What if 3I Atlas isn't anomalous? What if it's normal for interstellar comets, and our solar system comets are the unusual ones? Our solar system formed from a specific molecular cloud with specific properties. Every comet we've studied in detail formed here. If the conditions in our protoplanetary disk were atypical in some way, the comets produced could be unrepresentative of comets generally. Other star systems might routinely produce comets with different compositions, different structures, different strengths. If that's true, then as we detect more interstellar visitors, we might find that each one behaves differently, that there's enormous diversity in cometary properties reflecting the diversity of formation environments across the galaxy. This would make prediction vastly more difficult. Instead of having a few well-understood comet types, we'd have a nearly continuous range of properties. Every interstellar object would need to be assessed individually, and predictions would carry enormous uncertainty until enough data was gathered to characterize that specific object. Dr. Carrie Lease from Johns Hopkins Applied Physics Laboratory suggested in a February 2025 discussion that we may need to fundamentally rethink our classification schemes for small solar system bodies, potentially adding new categories specifically for interstellar objects that don't fit neatly into existing frameworks. So, what do we know for certain? Comet 3I Atlas is the third confirmed interstellar object detected entering our solar system. It survived a perihelion passage at 0.039 astronomical units despite predictions of 90+% probability of fragmentation. The nucleus remains intact more than a month after closest solar approach. The rotation period changed during perihelion passage in ways not easily explained by standard outgassing models. What don't we know? Why did every prediction fail? What is the internal structure of the nucleus that allowed it to survive? Are the surface features real? And if so, what created their regular distribution? Is this behavior normal for interstellar comets or exceptional? What does this tell us about the formation environment beyond our solar system? And here's the urgency. We have approximately 2 years of good observing time remaining before 3I Atlas becomes too faint and distant for detailed study. Every observation matters. Every piece of data helps constrain the possibilities and narrow down explanations. Because if we can't explain 3I Atlas, if this comet remains a mystery after exhaustive study with the best instruments humanity can bring to bear, That tells us something profound about the limits of our understanding and the surprises the universe still holds. The truth is this: we've never encountered an object quite like 3I Atlas. We've never seen a comet survive conditions that should have destroyed it while simultaneously exhibiting behavioral changes that standard models don't predict. We've never had to confront the possibility that our entire framework for understanding comets might be fundamentally incomplete. And the only way to resolve this mystery is to keep watching, keep measuring, keep analyzing, and remain open to the possibility that the universe is stranger than our models suggest. If this video left you questioning what else we might be wrong about, don't forget to hit that like button and subscribe to this channel. We're tracking 3I Atlas in real time as it leaves the solar system, and you won't want to miss any updates as new data comes in. Leave a comment with your theory. Is 3I Atlas proof that interstellar objects are fundamentally different, or just an extreme case of normal cometary behavior? And share this video with anyone who thinks we've figured out how the solar system works. After this, they'll realize how much we still don't know.